start. Good morning.
Good morning.
How's everybody doing? Doing okay? What's the cell phone rule?
What's up?
What's the cell phone rule?
What's it for?
So what's the cell phone for? No, what's the cell phone rule in this class?
Sorry.
No, what is it?
I'm not sure.
You're not sure? Somebody help me out. Who remembers what it is?
Have it out.
What's it?
Computer out.
What's that?
You don't have it out. You don't have
No, it's in
computer out.
high school. Professional discretion is what I call it. This is, I don't mind if you have your phone out, but you have to pretend like you're hiding it from me. Does that make sense? So you have it down here. Just don't be doing like this, like right in front of your face, right? Pretend that you're hiding it from me. Okay. Are there any questions, comments, concerns? Hopes, dreams, fears?
Assignment 1 is due the 4th. Am I right?
What's up?
Assignment 1.
Yes, the first assignment is due this Friday at midnight. We've already had a bunch of people turn them in. Hopefully you guys have all at least started. Well, we're into chapter 2 now, so hopefully we're done with the chapter 1 assignment. But I understand if we haven't finished it yet. So don't forget that's due Friday at midnight. Make sure that don't take photographs of your assignment. Make sure you scan it. And when you scan it, make sure you take the time to make sure your scan is of the paper. If your scan includes all the extra crap on the outside, the spirals of your notebook or the stuff around it, the scanner will still kind of treat that as a photograph. And your file size will be 4 times what it ought to be. And Blackboard won't accept your submission. And then you'll be sad. So, yeah. If your file size should be in the ballpark of 1 to 1.5 megabytes. If they're 3 to 4 to 6 megabytes, like some people have been turning in, or trying to turn in, Blackboard won't accept your work. So.
Well, you'll send you an error or something?
What's up?
It'll send you an error or something?
It'll send you an error, yeah.
Okay, that's
But most importantly, it won't make it to the grader, right? So your assignments don't come to me. I have it set up so they just go directly to the person grading, and they take care of it, right? So they won't know that you did your assignment, email it to me. So make sure you take care of that. Make sure your stuff actually gets submitted on Blackboard. And the best way to make sure that happens is, do it before 11:50 on Friday night, and you won't have any problems. Cool. Any questions about that? All right. Now the chapter 3 assignment is available now because we're going to wrap up chapter 2 today and pick up with chapter 3 on Friday. So like I said, if you haven't done the Unit 1 assignment just yet, you might want to get on it because you're a little bit behind the curve.
Assignment 2 is due the 9th, right?
What's up? Assignment 2 is due next Friday. Then assignment 3 is, next Friday is the 11th. Assignment 3 is due the next Monday, actually. So, yeah, so make sure you stay on top of that. Any questions about any of that stuff? Someone on Discord asked, can we write out the assignment on computer and submit it, or does that have to be handwritten? You can do it any way you like, as long as you're showing your work. Okay. What were we talking about last time? What's that?
Fundamental laws.
Yeah, we talked about codes, and we talked about those fundamental laws of Boolean Algebra. We kind of rushed through them, so what we're going to do first is we're going to kind of go recap. I'm going to list all those laws again, and then we're going to see them put into practice, and we're going to simplify some Boolean expressions. So, the first group of laws, play real quick, operations involving 1, 0, and 1. X or 0 is equal to what? X, good. X or 1 is equal to what?
1.
1, good. X and 1 is equal to what? X. And X and 0 is equal to what?
0.
Equal to 0. Good. So 0. Next up, we're called the idempotent laws. Which means an operation involving itself. X or X is equal to what? X. And X and X is equal to what? Also equal to X. Involution. x inverse and inverted again, what do we get?
X.
We get x back. Good. The associative law says that we can switch up the order of all these things. Associative. So x or y is equal to y or x, and x and y is equal to y and x. Commutative law. Wait, did I get it backwards again? I did. Then when I wrote my notes, and then again just now. It was backwards in my brain. That's commutative. The word commutate, which means to rotate, and then the associative. Which is quantity x or y or z is equal to x or the quantity y or z. And also quantity x and y and z is equal to x and the quantity y and z. The distributive law. Remember, there's two of them. The first one, x and the quantity y or z is equal to x and y or x and z. And the second distributive law is x or y and z is equal to x or y and x or z. And then finally, De Morgan's involves complementing functions, complementing expressions. Says that the quantity x or y inverted is equal to x naught and y naught, and the quantity x and y inverted is equal to x naught or y naught. All right, those are the ones that we jotted down on Monday. They're pretty simple. The only thing to do is just commit them to memory, right? And most of them make intuitive sense when you stop and think about it. Any questions about these guys? Yeah, what you got?
We need to memorize the complementary one too,
Oh, did I forget one? I did. I forgot my notes too. Because it wasn't in the summary. And that was complementarity, right?
Mm-hmm.
Which said that x or x naught is equal to what? 1. And x and x naught is equal to 0. Good catch. There we go. That's all. That's an important one to forget. All right. Any other questions? Okay. So these are the sort of basic mechanics that George Boole came up with when he defined Boolean algebra. Remember, the whole point of learning Boolean algebra is so that we can take our large, complex logical expressions and simplify them. Stuff that's sort of cost-effective to build. So to that end, we have a series of what we're going to call simplification theorems. And again, you just need to have them memorized. All right, the first one. It's called the uniting theorem. And it says that if we have x and y, or x and y naught, what's that going to be equal to?
Not 1.
What do you think?
1.
Not 1. It's equal to x, right? Because it's x and y, or x and not y, which means the y is sort of irrelevant, right? So yeah, so x and y, or x and y naught, is just equal to x.
What does it say? Right?
Uniting.
Uniting, my bad.
Yeah. And its counterpart, also x or y, and x or y naught is also equal to x. It's uniting theorem. Right. That's pretty powerful stuff, right? Because we can take an expression that's got 4 literals in it and reduce it down to just 1. Pretty solid simplification. We're going to use it a lot in this class. Number 2, it's called the absorption theorem. Not quite as powerful as uniting, but still pretty good. It says if we have x or x and y, that's just going to be equal to x. So x or x and y is equal to x. And then its other side is if we have x and x or y, they're also equal to x. Any questions about that one? All right. All right, CC.
Yeah.
The third one is called the elimination theorem. Elimination theorem, and it states that x or x naught and y is equal to x or y. So, does everyone see the difference between elimination and absorption? They look very similar, but they have a key difference. What's the difference?
The little.
X not y not?
Yeah, exactly, right? Wait, say that again?
Like it's x prime and not y prime?
Well, here, so I'm talking about this one right here and this one, and I think you said it. Yeah, right? Elimination has x naught anded with y. Absorption just has x anded with y. Other than that, they're the same expression. Right? That's the key difference. Don't mix the two up. Questions about that? All right.
Is there a key difference in those ones?
What's that?
There's a key difference.
Yeah, elimination theorem is x or x naught and y.
Oh.
So the inverse of x. Whereas the absorption theorem is x or just x and y. Elimination theorem has the x inverted. All right. And its counterpart, x and x naught and y is equal to x and y.
So when does the counter ever take place?
Say it again.
Like when do we need the second one?
The second one's
Yeah.
when we have expressions that look like the second one.
Oh, okay.
Yeah, we're going to see both sort of forms.
Yeah.
We'll see some of those forms today, too. All right. And last, the granddaddy of them all, the consensus theorem. The one that freaks everybody out. All right. And it is x and y, or x naught and z, or y and z is equal to x and y, or x naught and z. It has no counterpart, or at least not one we're going to talk about right now. All right, we'll have a whole class dedicated to the consensus theorem later, but for now, just memorize the form. Ooh. All right. So those are the 4 simplification theorems. Are there any questions about them?
Nope.
Cool. All right. Let's do some stuff. Can I erase this out?
Yes, sir.
All right.
Awesome.
Yes.
Can you explain the uniting theorem again?
What's that?
Can you explain the uniting theorem again?
Can I explain the uniting theorem again? I can state it again. All right, so the uniting theorem says that x and y, or x and y naught, is equal to x. On the flip side, x or y and x or y naught is also equal to x. So not much to explain on that, I think. Yeah.
Is it because the y's cancel each other out?
What's that?
Is it because the y's cancel each other out?
It's not that they cancel each other out, right? There's no canceling out is sort of a dangerous phrase, right? But you can sort of think of it logically as the y's are irrelevant. Yeah? So if it's x and y or x and the inverse of y, then it really doesn't depend on the y, right?
Yeah.
So I'll throw it out.
Remember it.
What's that?
That's a better way to remember it. It doesn't depend on what. So
I didn't understand anything you said.
that's a good way to remember it is x doesn't depend on y, so it's equal x.
Yeah. I dig. Cool. All right. So let's do a couple examples. Here we go. We got z is a function of a, b, and c. Is equal to a naught and b and c or a naught. What's its inference? So the first thing you have to do is look at that and then look over here and say, well, what is over here that kind of looks like that? Someone says something? 4? Use the names. Consensus?
Consensus, yeah.
All right, well, what do you think? Why do you think it's consensus?
It's pretty long.
Because they're pretty long. It's not consensus.
Absorption.
Absorption, fantastic. So, absorption all right, we've got it over here listed as number 2. It says x or x and y is equal to x. In this case, if we do a substitution, say let x is equal to what?
A naught.
What's that?
A naught.
It's equal to a naught, right? Because see, it's the only one that's out here by itself, right? Absorption, x is the one that's by itself. So x is equal to a naught. Y is equal to what? What's that?
B and C.
Yeah, B and C. So we can, when we do these substitutions, we can substitute by combining terms. So y is equal to B and C, which means that z is equal to what? A naught. Good. Yeah. That's all there is to it. Yes?
Do we have to do it that way?
What do you mean, do we have to do it that way?
Like substitute and stuff like that?
What do you mean by have to?
Like what if we did it a different way?
What different way would you like to do it? You got a different way in mind?
I took out the A naught and made it A naught parentheses B, C, and 1, essentially. And
Chase that rabbit. So you use which property? Which law?
Distributive.
Yeah, it's distributive. So you said A naught, B, C, or A naught. So you factor out the A naught, right?
Mm-hmm.
So you had A naught and B, C, or 1.
And then B, C, or 1 just becomes 1.
Right? Because of what?
I don't remember which one
Say
there is.
again?
Operations involving 0 and 1.
Yeah, operations involving 0 and 1. So that said that A naught and 1. Are you done yet?
Then it just becomes A naught. Because
Why?
A naught and 1 is just A naught.
Okay. Now, is this also a valid way to solve the problem? You bet. Is one better than the other? Not necessarily, but one has the distinct advantage of being done all in one step, right? We said uniting theorem, bam, there's the end. Yeah? Whereas this took, what, 1, 2, 3 steps to get it done. The reason the simplification theorems exist is because these kind of lock up really common operations, right? If you didn't have that, you would do this bit where you like factor a thing out, or 1 becomes the thing, over and over and over again, 5 or 6 times in the same like simplification, right? So what they've done is said, all right, well, this is a really common thing. We know what the solution is going to be, so let's just call it the uniting theorem and just do it in one step. Does that kind of make sense? Cool. Yes, sir.
Wait, if z equals not a, does that mean z equals x? Is that how it is? Or like, it's completely different?
So,
You know what I mean? Like x equals not a, then z equals not a. So
Yeah.
that means z equals x.
so you could say z equals x because we've already said that x is equal to not a.
Oh.
Right, but really, since z is a function of these things, a, b, and c, right? This bit over here is just to illustrate how the theorem is applied. Yeah? But the answer is still a naught, not x. It's confusing for you, right? All right, any other questions about this one? All right. Can I erase this example so that I can keep those guys up on board? Yeah. Or you can just speak up, you don't have to raise your hand.
Okay, why is BC equal 0?
Why is BC equals 0? BC isn't equal 0. Where is BC equal 0?
That was a question.
I'm responding to the person.
Okay.
I think I know what they mean. I'm going to guess that they're saying BC is equal to 0 because they're looking right here. And they're thinking BC plus 1 is equal to 1. How the hell did that happen? It's not plus 1, is it? It's or 1, right? Totally different mathematics that we're doing. This is not BC plus 1, it's BC or 1. In which case, anything or 1 is equal to 1. If that's not what you mean, yeah, speak up. Alright, let's do a good one. That one's too easy. Do this. Z is equal to A or B naught and C or D or EF. And all that and A or B naught and C or a quantity D or E and F not fluffed off. Simplifying Z. Maybe it can be done in one shot. It can be done in one shot.
A or B naught and C?
What's that?
A or B naught and C?
How'd you get that?
United theorem?
The uniting theorem. Right on. Now you're not just sitting there with the textbook open in front of you, answering all these questions, right? So where's the fun in that? But you can write. That's the advantage of being a remote student. Okay, so uniting theorem. X and Y, or X and Y naught is equal to X. In this case, what is X equal to?
A and B naught C.
Alright, yeah, stop doing that. It's not A plus anything.
A and B naught
A
C.
Yeah, or B naught and C, right? So notice, yeah, we got A or B naught and C, or this stuff, right? And A or B naught and C, or that stuff inverted. In fact, I used the wrong thing here, didn't I? Yeah, right, I should use the other one. X or Y and X or y naught is equal to x. And so yeah, in this case, x is equal to a or b naught c, and y is equal to what?
D or EF.
Good. D or E and F. So even though this is kind of a long, sort of intentionally gross-looking expression, look for the places where the things repeat. So the answer is z is equal to a or b naught and c. Any questions about that one? All right, let's do one more. Yeah, what's up? All right. I'll let this guy C is equal to A, B, or C, and B naught D or C naught E naught or A, B, or C. What does that simplify to? And you on the Discord, you gotta let somebody else answer. Not consensus.
It's elimination.
It's elimination. All right. What's our x?
A, B, and C naught.
A, B, and C naught. I don't see an A, B, and C naught up here.
A, B, or C naught.
All right, A, B, or C. Well, A, B, or C naught. Talking about this guy, right?
Yeah, that guy.
All right. It's important. You gotta get your words right. So yeah, it's elimination. Now this one tries to be a little misdirecty, right? By making the
first one.
the thing, the x, the inverted term, right? So that's x or x naught y is equal to x or y. In this case, we're going to let x equal what?
A, B, or C, all of it not.
A and B or C in quantity inverted. And y is going to be equal to what?
B naught D or C naught E naught.
Yeah, this guy right here, B naught and D or C naught and E naught. So, what's Z equal to?
X or Y.
What's that?
X or Y.
Yeah, in terms of the variables in the expression.
A, B, or C, all of it not, or B naught D or C naught E naught.
Here we see A, B, or C naught, or B naught D, or C naught E naught. Do I need to put B naught D or C naught and E naught in parentheses in my result? No, right? Cool. All right, questions about that one?
Yeah,
What's up?
why do you make the A, B, or C not X instead of A, B, or C?
Because that's not the one that's floating out, remember? So the theorem is X or X naught and Y, right? It's not about the inversion, it's about its place in the expression, right? This is, so here the x is out by itself and it's ORed with x naught and y, right? This is the term that's out by itself. And it's ORed with itself inverted. Remember, anything inverted is still itself again. Yeah? So this is still the inverse of this term. And that's the one that's out by itself. Cool. All right, any other questions about that? All right. Oh yeah. Well, not last time. All right, now is this?
Yes, sir.
All right, is everything? We'll move on. All right, so to make life a little bit easier, there are two standard forms of Boolean expressions. And oftentimes, we will try to get our expression to one of these two standard forms before we take the next step, right? We'll get it to a standard form and then we'll simplify it. It just makes life a little bit easier. The first standard form, and one we'll use most often, is called sum of products. Or SOP. And the second one is called product of sums. POS. All right, so let's talk about sum of products first. Sum of products. So by definition, a sum of products is a Boolean expression in which all the products are terms of a single variable. And what I mean by that is, an expression looks like this. For example, A and B naught, or C and D naught and E, or A and C naught and E naught. So we say sum of products. It's kind of again, the language sort of confuses the fact that it's not regular arithmetic, right? So it treats the ors as sums and the ands as products, right? So it is a sum, so this plus this in notation, right? This or this or this, of product terms of groups anded together, and only of single variables, right? So only, each variable only appears one time in each term. Does that kind of make sense? That's kind of a roundabout way to say it. But yeah, so when we say terms, we're referring to these guys. Now, terms can contain only one variable. So, for example, we could have something like this: A and B and C naught, or D, E, and F and G, or H, right? We have just one variable hanging off by itself. That's just fine. We also have a bunch. We have something like this: A or B naught, or C, or D and E naught. Right? All three of these guys are sum of products expressions because they contain only and terms, product terms, that are ordered together, and each term only contains a single instance of the variable, right? Yes?
So is that to say you couldn't have like two A's in the same term?
Correct. Yeah. So you couldn't have, you know, A and B. Right now that would make a lot of sense, because what's A and A?
Okay.
Just equal to A, right? So that would simplify to just A and B. But both are valid Boolean expressions, just one is not in the standard form, the other is in the standard form.
SOP is just one at a time, only one of A, one of B, and not one person. That's
Yes. Yeah. Or none of them. So, for example, put it this, A or B, and C, D, or E, F. Is that a sum of products expression?
Wouldn't it be multiple A?
What's that?
Wouldn't it be multiple A?
Well, yeah, it's kind of multiple A's when you distribute, but also
There's a and.
you get this or thing that's kind of messing things up, right? That's inside the term. Right? The term has to be uniform. Just ands, a bunch of ands, or with a bunch of ands, or with a bunch of ands. When you have this thrown in the mix, this or expression, that messes things up. Now we can obtain a sum of products, and here's the important part. If you weren't paying attention before, pay attention right now. Right? I'll write it this way. A sum of products can be obtained by applying the first distributed property. Right? One that said X and Y or Z is equal to X and Y or X and Z. Your textbook calls this multiplying out the expression. So if we were to do, here, can I erase like this stuff right here? Just focus on this example. Okay. I'm writing this up here. A or B and C, D, or E, and F. Right, we want to get it to standard sum of products form. We look at it and say, no, that's not standard sum of products form. We're going to multiply out by applying the first distributive rule. X and Y or Z is equal to X and Y or X and Z. So in this case, my first question, do we need to care about the E and F right now? No, it's taken care of, right? It's already set up to be sum of products. It's this thing that's messed up. So in this case, what is our X going to be?
CD.
Yeah, X equals C and D. Our Y is going to be equal to what?
Good.
All right, does it matter which one we pick, A or B? No. We'll say that Y is equal to A, Z is equal to B. So this expression now simplifies to A and CD, or B and CD, or E and F. And is this in standard sum of products form? You bet. All right, any questions about that? Good. All right. Like I said, just hit it with that distributed property stick. That's how you get it to where you want to go. All right. Let's do the other one now. Product of sums. Let me start over here. Concept is exactly the same, it's just sort of flipped over. Product of sums. This. And that's going to look like something like this. It's going to be some terms that are ANDed together that still only contain one instance of a variable. So this, A or B naught and C or D naught or E and A or C naught or E naught, right? In this case, our terms are these guys in parentheses. They're being ANDed together. Cool?
That's easy to solve for.
What you got? All right. So you speak about all louder. What they're used for? We're going to use them a lot, right? So because we want sort of algorithmic ways to design our systems, this gets us a place to start from, right? And when you sort of take a first pass at deriving your Boolean expression, it's going to be messy. It's going to look weird, right? And so if you want to get to that optimal solution, the best way is to first get it into a form that you're used to working with, right? And the ones that we commonly use are these two, sum of products and product of sums. So what you would do is you would take your raw, unfiltered Boolean expression, get it to one of these standard forms, and then simplify it. That's the purpose. All right. Just like before, we can have single expressions. We can have something like this, A or single variables in a term, A or B, C or D or E, and F, right? We have one variable sort of sticking off by itself. It's being ANDed with everything else. Everything's fine. This next one looks a little bit more confusing, but it's still valid. If we had A, B naught, and C, and D naught or E, right? This is also a valid product of sums form. How many terms does this one have? 4. It's got 4 terms, right? Everything's being ANDed together. This one, this one, this one, and that one, right? Simply because it just has one variable doesn't make it not in that standard form. All right, what about this guy? A or B, and C or D, and yeah. What's that? Close parentheses.
No.
Is that in product of sums? Nope, it is not. Why not? Yeah, it's because it's or term over here. In the same way we had that ANDed term on that guy, so we're messing things up. So, go ahead and put it down here. Actually, can I erase this definition? Give me like one more chalkboard. So the sum of products is obtained by multiplying out and using that first distributive property. Product of sums is obtained by applying the second distributive property. All right, this is the one that is x or y and z is equal to x and y and x or z. So x or y and z is equal to x or y and x or z. Textbook also calls this one factored. So just kind of like regular algebra, to get that sum of products form, we want to multiply everything out using the first distributive property. To get product of sum form, we want to factor everything out using the second distributive property. So let's go ahead and work this one out the way we just did this one. Okay, so what do we have? We have A or B and C or D or E and F. And I'll go ahead and just keep this over here. X or Y. Z is equal to X or Y and X or Z. Now this one's tricky. This one is not sort of immediately obvious, right? I was going over my lecture notes this morning. I hadn't finished the coffee yet, and I was looking at this one. What's this example? but it's there. So like before, we're gonna do some substitutions. What is our x?
Yeah.
What's it?
E and F.
E and F, good. What is our y?
A and B.
A and B, or A or B. And what's our z?
C or D.
C or D. Good. All right. Maybe it wasn't easy. Maybe I was just sleeping this one. Okay. So what do we get? After the substitution, what happens next? That's it.
Is that letter E or F, or is it a multiplication?
So there's no multiplication, and we shouldn't have E or F yet.
EF or A and EF or A or B, all that multiplied by EF or C or D.
So we're not multiplying anything, right?
Any.
Right. And what were you gonna say? That thing? Okay. Yeah. So it all kind of works out. We have A or B or E and F, and C or D or E and F. Right? Are we done? Is this in product of sums form? See some nodding of heads. See some shaking of heads. Who thinks we're done? Just okay. Be brave. Who thinks we're not done? Ooh, class thinks. It's not done.
Okay.
Right? Because we still have this and hanging out inside of our term. So what do we need to do now?
Figure it out.
What's that?
Take it out.
Take what out?
Yeah.
Use the second distributive property again.
Yeah, we choose it again. But not only do we do it again, we have to do them sort of to each one separately, right? So on this first one, A or B or E and F, what is x equal to?
A or B.
A or B, good. And y is equal to E. Z is equal to F, right on. Could Z be equal to E and Y be equal to F?
Yeah.
Yeah, we do this fine. Okay, so put that together, that's going to get us A or B or E and A or B or F. Now on this side, what's our x equal to?
C or D.
C or D, good. And our y is equal to E. And our z is equal to F, good. And that gives us C or D or E and C or D or F. Now that big long monster is our final product of sums solution. So yeah, just gonna apply that distributive property over and over and over again until you can't anymore and you have your final solution. Cool. All right, any questions about that? All right, if there are no more questions, we'll pick it up right there on Friday. Have a good rest of your day. Thanks, guys.